Hello, everybody. Today we'll start a new chapter, CMOS. It's very, very, very important chapter for digital electronics, especially for digital electronics, and of course for analog electronics also. We'll start by introduction, then the basic logic gates. CMOS comes from complementary metal oxide semiconductors, CMOS. Okay? So complementary metal oxide semiconductor was fabricated by Tang and Frank at Fairchild Semiconductor in '63. So in '45, they fabricate MOSFET. Then after around 20 years, they invent or fabricate CMOS. Till now, CMOS is a logical family that uses N channel and P channel MOSFET. So they use CMOS circuit, they use MOSFET, but with some conditions. They will use both at the same time, N channel and P channel. In this family, the special construction of the circuit and the golden rule of the CMOS circuit, and for the good design inside digital circuit, is used as a pull-up. Will use PMOS in pull-up load device, while NMOSFET as a pull-down device. We'll explain more about that. Okay? We have PMOSFET on the pull-up network, NMOSFET in pull-down network. We'll talk about this later. The low power dissipation of CMOS, because we use this golden rule, so the low power dissipation of CMOS has made battery-powered wristwatches and hand-led calculators possible, as well as recently developed notebook, computers, laptops, embedded system, IoT device, and so on and so on, healthcare application inside the hospital, everything, IoT device, and every small applications of small devices. They use CMOS because has low power dissipation. So CMOS technology is used in, of course, microprocessor, microcontroller, and memory chips, including CMOS BIOS inside the motherboard, and other digital logic circuits. Also, it's used for analog circuits, such as image sensors, CMOS sensors, and others. So, because SAD, complementary metal oxide semiconductor, complementary means at the same time will use for the same wafer, same circuit or board, at the same time will use NMOSFET plus PMOSFET. Because they are complementary, when we put NMOSFET with PMOSFET together, we call it CMOS. Okay? So this is the advantage of CMOS. We will see more advantage, of course. So because of that, CMOS is used for very large scale integration, VLSI chips, till now, till today, till now. Okay? All your mobile phone except some of one, okay, using CMOS processor or CMOS transistor inside. All our mobile phone. Okay? We'll talk about them later. Okay? So for the very large scale integration means VLSI circuits, Very large scale integration means very small circuit. Okay, so now we're talking about nanotechnology fabrication in nanometer size, the transistor in nanometer size. As of 2011, so from 63 to 2011, 99% of all IC integrated circuit chips are fabricated using CMOS technology. Imagine the big production of CMOS. Since 1963 till 2011, they used 99% of all circuits, computer and other computers, or of all circuits, analog, digital, they use CMOS technology. After 2011, a new update transistor released, like FinFET and CNFET and others. So before 2011, no new transistor technology. They use from 63 till 1963 till 2011, all of the circuit are CMOS. Till now we use CMOS, but the percentage is small decrease, around 85. Around 85 of all circuits are CMOS today. Two important characteristics of CMOS devices are, focus here, high noise immunity. High noise immunity means that the CMOS transistor can hold noise, high noise. Compared to MOSFET or to BGT, CMOS transistor can hold more noise, high noise, without corruption or errors in the output. So this is called high noise immunity. And at the same time, low static power consumption. Very low static power consumption. As you can imagine, in CMOS technology, in CMOS circuit, only one transistor of the MOSFET pair, N MOSFET or P MOSFET, is always off. So at the same time, we will not see that P MOSFET and N MOSFET are turned on at the same time. One of them is turned off, and one of them is turned on. That's why has the CMOS technology, the CMOS transistor has very low, it's not low, very low static power consumption compared to other transistors. So that's why CMOS transistor consume over 7 times less power than N MOSFET and about 100,000 times less power than TTL, BGT TTL. Imagine that. Imagine 100,000 less power than TTL. Imagine that. And between quotation, CMOS always use enhancement mode of MOSFET, because CMOS are usually used in digital electronics more than analog electronics. And in 1975, Moore's law, the Moore's, which is the Intel CEO, said at 1975 that the number of components per chip will double every 18 months. Every 1.5 years, the chip, the transistors inside any chip will be doubled. It's true till 2011 or 15. Okay, so now the transistor scaling. Before in 70, first in BGT, in BGT transistor, and starting of CMOS transistor, the size of the transistor was 10 micrometer. 10 micrometer. Okay. Then the scale is decreased every generation. They decreased. Okay. Till now, above 2000 year, at the year 2000 till now, we call it nanotechnology, VLSI. So in nanotechnology, the size of the transistor was 10 micrometer. After 2000 of the year of the 2000 becomes 100 nanometer and 60 nanometer, 65 nanometer, 32 nanometer. Till today, in this month, the company Samsung released 3 nanometer transistor. The first company in the world today, Samsung released the first transistor 3 nanometer. Okay. So, but the basics now, the basic CMOS scale now in our mobile phone, even the Samsung mobile phone, the ordinary versions of Samsung mobile phone or memory is 32 nanometer. 32 nanometer or 28, something like that. But they invent today, Samsung company, they invent 3 nanometer transistor. We'll see it later in our lectures. Imagine that example of this Intel before in 85, the Intel motherboard or CPU. Okay, this is 8383. Okay, it's CPU microprocessor. Okay, has 2,075,000 transistors, and the size is 104 millimeter square. After 4 years, only 4 years, imagine that. After 4 years, okay, after 4 years, becomes 1 million transistor in the same chip. Not in the same chip, sorry, in 17 millimeter square. So in 17 millimeter square, they put 1,000,000.1 transistors. Okay, before 4 years, in 104 meter square, they put 275,000 transistors. Imagine that. Today, in 19 CMOS, using CMOS, in 19, Intel using 10 nanometer technology CMOS channel, okay, in CPU circa, they put more than 100 million transistor in each millimeter square. Imagine that. So for the big motherboard or for big CPU will contains more than 10 billion transistors. Okay, we talk now about only CMOS technology. So imagine that. Here we have a wafer. This is called wafer, okay, for CPU. So this is the CPU, okay, old CPU. It's not a new CPU. It's old CPU, okay. The old version of CPU, okay. We have inside it multi-layers of wafer. This is called wafer, okay, multi-layers, okay. Each layer has section. This is the cross section of the transistors. Here in this processor, they use transistor with 50 nanometer size. Okay, today we have 3 nanometer size. Imagine the numbers. Okay, so this is inside the CPU. Now, please, this is very important slide called golden rule in CMOS design. So the only one rule, we have only one rule in CMOS transistor. We have only one rule, but it's a golden rule, which is all the inputs will enter both networks, pull up network and pull down networks. Okay, pull up networks means sub-circuit here. We have two sub-circuits. Sub-circuit 1, which is called pull up network and connected directly to VDD and will contain PMOS. And we have pull down network, which is connected to the ground and contains only MOSFET. So imagine that we will not put PMOS to the ground and we will not put NMOS to the VDD. So all the transistors, all the PMOS transistors together will be connected to the VDD, and all the NMOS transistors will connect it to the ground. Here the golden rule will be all the inputs must enter, all the inputs must enter both networks. We will not see any input can enter one of them. Okay, so we'll consider it as bad design. So for good design, CMOS design, and for FinFET transistor, also for CNFET transistor, they use the same golden rule. For VN, it must all inputs enter both networks, pull up networks and pull down networks. Pull up networks must be contains only PMOSFET, and pull down network must contains only NMOSFET. So, and the output will out from the middle of the both networks. So the input must enter both networks and the output must be between both networks. The output will not be below or above. So this is the golden rule. Okay. Now for this truth table, for the input 0 volt, low voltage input, MOSFET will be off, PMOSFET will be on. For high voltage, when the V input equal VDD, the MOSFET will be will be on, and PMOSFET will be off. So as you can see, one of them will be turned on and other will be off. No, we don't have the state that both transistors will be turned on at the same time. So that is the big advantage in any circuit. Why? We'll see why here. We'll see why here. So I will repeat. In VLSI circuit or nanotechnology circuit, we will not use resistors. No resistors for VLSI circuit. Why? Who tell me why? Why? Guys, who will tell me why we don't use resistor inside small circuits, VLSI circuits?
يصير في disadvantage.
Disadvantage, yes, but what is the disadvantage?
بينقص الاوتبوت.
Others أهم. VLSI very large scale. انتبهوا على السايز، عم نحكي سايز هون. Very large scale integrated size. VLSI means small, very small circuits. Resistor at this size تبعه. Size of resistor, what is the difference between if we compare the size of resistor and the size of transistor?
دكتور
إذا
يمكن
ما
لأنه
نشيل 1
الترانزستور
ريزيستور فينا
بده
نحط 1000 ترانزستور.
سوري عيد شلت.
إذا شلنا 1 ريزيستور فينا نحط محله مينيموم 1000 ترانزستور، فأكيد إذا نحط ترانزستور أحسن.
Perfect, perfect. Because the resistor has big size in millimeter or centimeter, and the transistor in nanometer. Okay, so we can replace one resistor by 1,000 or more transistor. That's why in VLSI circuit or nanotechnology circuit, we don't use resistors. This is for part A. Part A about the size, and part B about the heating. The resistor will heat, has more heat. So if we have more heat, means more power dissipation. More power means more energy. Okay, so because of heating and because of sizing, we will not use a resistor inside nanotechnology circuit or VLSI circuit in digital electronics. Okay, so this is example of inverter. Okay, this is CMOS inverter that contains at the same time, if we look to the graph, we have one MOSFET connected to the VDD at the top. This is called pull-up network, and one MOSFET is connected to the ground. This is called pull-down network. The input will enter at the same time both the transistors, and the output will be from the middle of two transistors or two networks. This is the typical golden rule of CMOS technology is CMOS inverter. So as you can see here, for V input 0, MOSFET will be off and P MOSFET will be on. So no current here. We don't have current. We don't have current. We don't have closed circuit here. We don't have closed circuit here. The VDD will not connect to the ground at all. So here we have one of P MOSFET is on and MOSFET is off for V input equal to 0. So here you can imagine this part is not exist. Off means not exist. So we have only VDD, one transistor output. So no current here. We don't have current here. That's the big advantage here. No current here. The output will be direct connected to the VDD without limitation. Without limitation that we see it before. Before we see limitation. Here we don't have limitation. So the output will be totally 5 volt. We call it the output high strong one. Strong one here, logic 1, okay? Logic 1, high voltage, logic 1. So strong 1 means the V output high is equal exactly 5 volt. No decrease in voltage because no current. We don't have current. And you know the power equal Ri. We don't have here resistance. Ri. Even we have resistance. I equal to 0. So power equal to 0. That's why the big advantage in CMOS is we don't have currents. No current, no power, or power almost 0, negligible power. So that's why the big advantage, especially in embedded system and our smart mobile or embedded system or IoT devices. So for input 0, P MOSFET will work and MOSFET will be off. The output will be connected to the VDD directly with a strong 1, 5 volt equal VOH. And the inverse. If the input is high, the inverse. And MOSFET will be on, P MOSFET will be off. So always no current here. Also in this step, we don't have current because VDD is out. When PMOSFET is off, means this part of the circuit is not exist, is off, okay, is high. So always we have here, output is directly connected to the ground and called strong zero, because in this time we don't have limitation in CMOS transistor like in BGT. In BGT, the limitation is 0.2 volt. Here in CMOS, we don't have limitation in the transistor. The out will be directly connected to the ground by zero value, because we don't have a resistor. Okay, we don't have resistor. If we have resistor, this zero value will be 0.01 or 0.02, like in MOSFET inverter. Okay, in CMOS inverter, we don't have resistor. So it's strong zero and strong one. As you can see, we did it at last. So in CMOS transistor and above technologies like CMOS, FinFET, CNFET, and others, new technologies, new transistor technology, we always have strong one and strong zero. Okay? No losses in voltage. So the CMOS inverter is typical, the golden rule of the CMOS technology. Now, for this example, if we use power MOSFET transistor, it's not CMOS, power MOSFET called IRF 830 for an MOSFET, IRF 9630 for PMOSFET. If we put these two transistor, MOSFET transistor, okay, but they are not CMOS, the power will be 0.031 milliwatt. Okay, I think you will do it in the lab, I think. Now, the comparison to MOSFET inverters. Before, in our old lecture, we have MOSFET transistor model 1 with resistor. The power will be 50 milliwatt. This is inverter number 1. This is inverter number 2. We replace this resistor by an MOSFET diode connected transistor. Act like resistor. The power will reduce, okay, 2.6 milliwatt. And we, in inverter number 3, we replace the diode connected transistor and MOSFET transistor to diode connected PMOSFET transistor. Also, the power is reduced 0.9 milliwatt. Now we use here the power MOSFET transistor. Now, for this power MOSFET transistor in this technology, if we put PMOSFET above at the top and N MOSFET at the bottom, input will be enter both of them, the output from the middle. So the power will be 0.031 milliwatt. Imagine that from 50 milliwatt using one resistor to 0.031 milliwatt without resistor. We use PMOSFET only. We replace that resistor to PMOS. Okay, this is for power MOSFET transistor. But in real life, in real data, if we use CMOS transistors, the power will be 0.0015 milliwatt. So around 33,000 times less than the first one. Okay, imagine the decrease in power and the heat and the size also. Of course, the size also. Any question here?
No, doctor.
Perfect. So نرجع. Here we use resistor. We replace resistor by diode connected transistor here or here. We decrease the size and we decrease the power. Okay, but in golden rule of CMOS rule that the input must be enter both of the transistor, like here, we replace the diode connected transistor by PMOSFET. PMOS. When we replace at the top PMOS, at the down NMOS, and we use the golden rule of the CMOS technology, the power will be reduced more than 33,000 times. Okay, so imagine this big advantage till today. Okay, now if we switch them, if we put MOSFET at the top, PMOSFET at the bottom, okay, we break here, we break the golden rule of the CMOS. Okay, if we switch them, what happens? What happens? For 0 input, MOSFET will be off, PMOSFET will be on. In this circuit, it's not inverter. This circuit is not inverter, okay? It's not inverter because for input 0, the output is 0, weak 0. Okay? So here, I will repeat. For input 0, MOSFET will be off, PMOSFET will be on, so output will be directly connected to the ground. Here we have limited by internal diode inside PMOSFET that work in contrary with the ground to raise the 0 volt to 0.5 volt. So here we have weak logic 0, weak 0. This 0 is not 0 volt, is 0.5 volt. Okay? And the inverse. For input high, MOSFET will be on, PMOSFET will be off. So now the output will be directly connected to the VDD, but limited by internal diode that is in reverse direction of the output, which is always 0.5. Here we add 0.5 volt. Here we have VDD minus 0.5 volt equal 4.5 volt. This is weak 1, the output high. So if we switch, always we must put PMOSFET, always we must put PMOSFET to the VDD to eliminate the internal diode 0.5 volt. Always inside the transistor we have diodes. Okay, so to eliminate the effect of the internal diode, that's why the golden rule of CMOS said always connect PMOSFET to the VDD and MOSFET to the ground to get strong 1 and strong 0. Else you have to add or decrease or add or subtract 0.5 volt. So if we put it here, PMOSFET to the ground, we will add 0 plus 0.5 volt. If we connect MOSFET to the VDD, to the power supply, we will subtract 5 minus 0.5 volt. Internal diode here is 0.5 volt. This is called buffer. Buffer, 0 input, 0 output, 1 input, 1 output. This is buffer, weak buffer design. This is weak buffer design. For strong buffer design, it must include 2 inverters in series. We'll stop here and we will continue next time. Any question? We'll repeat this.
No.
Next lecture, we'll repeat this. Okay. Any question?
No, doctor.
No, doctor, thank you.
Perfect. Okay.